Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Helen Raflis. Here, I want to explain my paper with title Application of Functional Expansion Trolley Filter in a Gas-Cooled Fast Reactor Design. Content. The content of my presentation are introduction, design and methodology, result and discussion, conclusion, and references. We start with understanding the candidate of nuclear reactor generation 4. There are 6 candidates of nuclear reactor generation 4. These are sodium fast reactor, lead fast reactor, very high temperature reactor, gas cooled fast reactor, supercritical water cooled reactor, and molten salt cooled reactor. In this research, we focus on the gas cooled fast reactor. Gas cooled fast reactor has potential for getting high thermal efficiency and fast-fuel cycle. It can utilize natural uranium during operation as blanket fuel, using helium gas as primary coolant, high working temperature, and low fire activity effect. Gas-cooled fast reactor is very similar to boiling water reactor system. They use single working fluid to directly connect it with fire turbine and generator to produce electricity. These advantages of gas-cooled fast reactor characteristics related to safety, sustainability, economic, and proliferation resistance. Our design is applying pin-type fuel. The pin fuel with metallic cladding is standard fuel for power reactor. The fuel is in the stack of pellet. Gases and volatile fission product will escape from the fuel pellet and trap in helium gas plenum. Monte Carlo code, we use OpenMC. The OpenMC is open source Monte Carlo code that provide the exact solution to solve the net transport equation in full-scale geometry and 3D model using affiliated nuclear data file and using continuous energy. OpenMC has capability in parallel computing with NPI and OpenMP and using Python programming language. The OpenMC version 0.12.0 that was released in 2020 enabled multiplication of the poly by a set of orthogonal functions that is legendary polynomial and Jernicke polynomial. The radial flux distribution of gas-cooled fast reactor has high energy neutron spectrum and possible occur in the center of the core. The objective is to understand the radial axial flux distribution for modular gas-cooled fast reactor using OpenMC code. The OpenMC tally system can calculate the following physical parameters, like flux, physical reaction rate, neutron production, surface charge. The functional expansion tally system method doesn't apply the traditional mesh scheme. We directly use discrete cell and mesh calculation to determine the spatial distribution of neutron flux. In this study, we implemented the legendary polynomial feature for axial calculation and Jernicke polynomial for radial calculation. We evaluated flux distribution from the traditional mesh and functional expansion tally feature. We performed 350 by 350 mesh and variation functional expansion tally order rank 5, 10, 50, and 100. Here, the general equation, general solution, and here, polynomial legendary from mathematical model, and this one flux along z-axis C, and this one order 10, and this one for Jernicke polynomial order of flux formula. Design and methodology. Figure 1 presents the radial layout of core design gas-cooled fast reactor, and Figure 2 shows the modeling of fuel rod and fuel assembly in XY fuel figure. Both of figures were generated by MATLAB Python model. The core configuration has 6 regulating control assembly, 3 shutdown assembly, and blanket inner core and shielding. Design specification gas-cooled fast reactor. Table 1 shows the parameter information of modular gas-cooled fast reactor design. The reactor design provides the thermal power about 250 megawatt thermal and hexagonal lattice configuration, has 127 hexagonal lattice for fuel assembly and full rod. Table 2 show the material information used in this analysis. The material composition in inner core used mic oxide fuel, blanket core used natural uranium, cladding used stainless steel HT9, coolant material is helium gas, reflector material the BEO, then shielding reagent used B4C. Table 3 provide the parameter information of fuel rod in modular gas fast reactor design. Result and discussion. Figure 3 and Figure 4 show the comparison of axial radial flux distribution between traditional mesh 350 by 350 and functional expansion feature order 10. From this figure, we understand that the radial axial Jernicke polynomial in functional expansion poly gives smaller flux distribution and be tailored than the traditional mesh poly. The two methods agree well in the center of both fuel region and the coolant channel. The flux distribution show the difference in behavior of flux toward to the reflector. This difference is due to truncation error, which result from approximating a piecewise smooth function in the functional expansion poly. Figure 5 shows the comparison of flux distribution with radial axial Jernicke order 5, 10, 50, and 100. The figures show that when the order of Jernicke polynomial is increased, there is an increase in smoothness and continuity of natural flux distribution. An order value that is too high will cause the flux distribution to fluctuate more. But if the order value is low, the flux distribution will obscure and natural flux distribution. The order value of 10 is the optimum value used in the following study. Figure 6 shows the radial flux distribution. This result just extract the Tolley coefficient and use radial only Jernicke polynomial Tolley flux distribution. The core design used radius about 125 centimeter and natural flux in order 10 when functional expansion Tolley method were applied. Figure 7 show the Jernicke radial axial flux distribution based on legendary polynomial coefficient and azimuth or radial Jernicke coefficient only, which allow reconstructing the flux in both radial and axial direction. The result informed that the time integral of each Jernicke polynomial is flux distribution with boundary condition in both radial and axial direction. We go to conclusion. We have investigated the application of functional expansion Tolley filter in modular gas fast reactor design. Here, we apply the legendary polynomial feature for axial calculation and Jernicke polynomial for radial calculation. This feature enables us to reconstruct the continuous function of space or angle from Tolley system. The finding demonstrated that the integral of each Jernicke polynomial flux time with boundary condition in both radial and axial direction give a good understanding of gas for design profile. Acknowledgement. This work supported by Indonesian Ministry of Research, Technology and Higher Education, Bapeten as High Research Grant and World Class Research ITB 2019. This is my reference. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.